So with respect to the stereochemistry of the TE2 reaction, the arrangement of the hydrogen in the leaving group really matters when you are doing E2 elimination. There are two ways that the CH and the C leaving group bonds to be coplanar. Remember that there is a free rotation around a carbon single bond carbon. So this is different than a carbon double bond carbon. A carbon single bond carbon has a free rotation. So I can simply go from this orientation where the hydrogen and the X are on the same side to this orientation over here by a simple rotation. We're going to call the orientation where the hydrogen and the halogen to be on the same side. This is called a syn periplanar. And when the hydrogen and the halogen are on opposite sides, this is going to be an anti-periplanar. This is different than cis and trans. With cis and trans, there's no rotation, so you cannot go from cis to trans. And with cis and trans, you do have a carbon double bond carbon in there to be called cis, and again a carbon double bond carbon in there to be called trans. So in order for the base to come and attack the beta hydrogen, there is a rule in there. And the rule says that E2 elimination happens whenever you have the hydrogen and the leaving group, they have to be trans diaxial with respect to each other. In another word, they have to be they have to be periplanar geometry. Anti-periplanar geometry, this means that they should be away from each other 180 degrees. This is another name for trans diaxial. In case you were working with a chair conformation, a cyclohexane chair conformation. Now the whole idea is to have a favorable E2 reaction. The base is gonna come, so this is the base with a lot of electrons, lone pairs in there. So that base with a negatively charged is going to come and attack the beta hydrogen. So this is going to be the beta hydrogen over here. If the hydrogen is on the same side as the leaving group is a bromine, chlorine, or iodine, so it doesn't matter. And the leaving group here has a lot of electrons. The base has a lot of electrons. So it doesn't make sense that the base comes and attacks the hydrogen that is on the same side of the leaving group. If this is the case, then you would have two electron-rich groups that are very close to each other. The base is an electron-rich group and the leaving group, which is an electron-rich group. These two will repel each other. The best orientation is for the base to be, or the hydrogen to be on opposite side of the leaving group. That way, that when the base comes and takes this beta hydrogen, it will not interfere or interact with the electron-rich leaving group. It's going to be 180 degrees away from it in a different plane, in other words. So it's a preferred geometry where the base comes, takes the hydrogen, form a double bond, and the halogen is going to leave from the other side. This is the stereochemistry for the E2 mechanism in there, where we say that the hydrogen in a cyclohexane and the leaving group has to be trans diaxial with respect to each other, or in other words, anti-periplanar with respect to each other. So let's consider this example. If we have chlorocyclohexane and I ask you which one of those conformations is going to have an E2 mechanism or elimination, which one of these conformations is going to undergo elimination. Well, we know that equatorial is more stable than the axial, and you can simply do a conformation in there, a simple flip of the chair conformation, and you can see that a chlorine here is on the equatorial, this is down, so you flip that, and then the chlorine will remain down. It will remain down in this case, but now it is in the axial. We said when you do a conformation, down remains down, but always equatorials change to axials, axials change to equatorials in there. The equatorial conformation is going to be the more stable conformation, but it doesn't mean that if you have a more stable conformation, your product is going to be more stable if it comes from this conformation. This is not true. One of those is going to undergo E2 elimination, the other one cannot undergo E2 elimination. So for E2 elimination to happen, the condition here is that my beta hydrogen and my alpha leaving a group has to be trans. They have to be diaxial with respect to each other. So the equatorial, with respect to the equatorial conformation, there is no way that we will end up having any E2 elimination. So there is no E2 elimination for the equatorial conformation. Reason why? Because the chlorine is on the equatorial position. I need to have E2 reaction. I need my chlorine to be on the axial, my beta hydrogen to be on the axial. So if I flip it, I'm going to end up having my second conformation in there where my chlorine is on the axial. So if the chlorine is on the axial down, then I do have in this case two beta hydrogens. And these beta hydrogens are the same, by the way. These two are the same. So I'm going to end up having just one product in there. So the base is going to come, see how it's doing it. Base is attacking this hydrogen, which is far away from the chlorine. So there's no interaction between the electron-rich base and the electron-rich leaving group. Base attacks the hydrogen, form a double bond, and the halogen is going to leave, and we're going to end up getting our alkene in this case. Question is, consider here the E2 dehydrohalogenation of cis and trans to chloro, 1-chloro to methyl cyclohexane. And let's see over here which one undergoes E2 mechanism. So there's one of them probably that undergoes, or maybe two of them that undergo E2 mechanism. Let's go ahead and see which isomer undergoes the E2 mechanism. We're going to consider the cis first. So with respect to the cis isomer, that exists as two conformations. So you take the cis, you draw both conformations in there. You draw the chlorine to be equatorial, flip it, and then it is axial in there. Remember the rule for flipping, up stays up, but whatever is equatorial is now axial. Whatever is axial is now equatorial. Up stays up, okay? For E2 elimination to happen, the hydrogen and the leaving group, they have to be trans-diaxials with respect to each other. I can easily locate my alpha carbon, the one that has a halogen in there. I want my halogen to be on the axial. I don't want it to be on the equatorial. So this conformation does not do any E2 reaction. No reaction in E2 reaction in this conformation, but there is an E2 reaction in here because my chlorine is on the axial, so I just have to find my beta hydrogen in this case. So here I do have my beta hydrogen. See the beta hydrogen in there. The beta hydrogen, this is my, basically I do have here, this is going to be my beta hydrogen, and that beta hydrogen is down. I do have another beta hydrogen in here. So let me see. Yes, I do have another beta hydrogen in there, which is also down. So here you go. I'm going to end up having two products in this case. The base can come. So the base can come and it can take that beta hydrogen. It forms a double bond here. Chlorine leaves. So my first product is going to end up having an alkene with, of course, my CH3 is on the equatorial, plus the other product is when the base here, okay, so this base can come, can take this beta hydrogen, form a double bond here, the halogen can leave. Notice that in both cases, the base attacks the axial hydrogens. And I chose the axial hydrogens that are 180 degrees away from the chlorine. So the base attacks the axial hydrogens one at a time, form a double bond, the halogen is going to leave. So the rule always to have an E2 reaction for the stereochemistry for the E2 mechanism in cyclohexanes, the hydrogen, the beta hydrogen in the leaving group has to be transdiaxials with respect to each other. So the product, when this base takes this hydrogen, form a double bond and the chlorine leave, the product is going to look basically like this. You do have a double bond, so the double bond is going to be here now. Okay, and then of course my CH3 is going to be here. This double bond, this alkene is different than this one. Which one is major? The one which is more substituted is the major product. And definitely it's that green one to be the major product, because locate your alkene. Around the alkene I do have 1, 2, 3 carbons. So this is a tri-substituted. Here, locate your alkene. Around the alkene I do have a 1 and basically a 2. So so this is going to be around the alkene, carbon double bond. This is going to be 1, this is going to be 2, so it's going to be a di-substituted. So definitely this guy over here is going to be the major product. This is what I was saying over here. So you're going to end up getting the 2 products. You can simply keep them as a chair conformation or change them into a cyclohexane planar structure. With respect to the trans isomer, draw the 1-chloro-2-methyl cyclohexane, flip it to get the axial conformer. And once you get the axial, now I know that this equatorial is more stable. I know that it's more stable, but it's not necessarily the one that's going to lead me to my product. The one that's going to lead me to the product is basically the conformer that has the chlorine to be on the axial position. And I need now to find a hydrogen to be on the axial position, adjacent beta hydrogen to be on the axial position. This is going to be my beta hydrogen over here. It's going to be my beta hydrogen, so it's going to be my only beta hydrogen that is going to be on the axial position. So now my base is going to come. That base is going to, okay, I should have written the base on the side. So the base is going to come, and that base is going to take that beta hydrogen, form a double bond, halogen is going to leave, and we're going to end up getting our alkene. So as a summary for the E2 mechanism, it's a second order reaction, it happens in one step. For the alkyl halides, tertiary alkyl halides, they are faster than secondary alkyl halides. Then primary alkyl halides, E2 mechanism happens with all, with tertiary, secondary, and primary. So if you want E2 to happen with tertiary and secondary, you have to use small bases or bulky bases. It doesn't matter. Any type of strong base, it works. If you want E2 to happen with primary, you have only to use a bulky base, like LDA or like potassium tertiary butoxide. This is the only way that E2 happens with a primary alkyl halide. So let's have an example here. What alkenes are formed from each alkyl halide by E2 reaction? So again, you have to check the type of alkyl halide that you are working with. So this alkyl halide is a secondary, this one is a tertiary, this one is a secondary, and this one is also a secondary alkyl halide, all of them. So they are asking about what alkenes they are formed. So all what you need to do is just locate your alpha carbon. So this is going to be my alpha carbon in here. I know that the reaction happens in one step there. So it's going to be my alpha carbon. And then locate your beta hydrogens. So I have a beta hydrogen in here. This is going to be beta 1 hydrogen. I do have another beta hydrogen over there. It's going to be a beta 2 hydrogen. So if the base comes and takes that beta 1 hydrogen, then my double bond is going to be here. Then let's go ahead and draw our first alkene. Plus if the base comes and take this hydrogen, then the double bond is going to be here so that the bromine leaves. Then I'm going to end up getting a double bond over here. And this is going to be the second. Now, with this isomer in there, with this product, alkene product, I do have a cis and a trans, because I do have basically the groups, the X and Y over here are different. So this is going to be a hydrogen here. This is going to be a hydrogen there. Normally, I highlight my hydrogens. These hydrogens are the same groups. So the same groups on opposite sides, this is considered to be trans. You have to write your cis product. So I'm just going to do plus over here. I can say plus the cis isomer or draw the cis isomer. So you have to draw it. So in this case, let's go ahead and draw that. And that is going to be my cis isomer. So that is going to be my cis isomer over here. Another example. This is going to be my alpha carbon. We highlighted this. This is going to be my beta. This is going to be my beta. So it's going to be beta 1, beta 2 carbon, and beta 3 carbon. And all of those are different. All of those have hydrogens. So this is a beta 1 hydrogen. This is a beta 2 hydrogen. And that is a beta 3 hydrogen. So if the base came and take this hydrogen, then my double bond can either be here, can be here, can be here. So I'm going to end up having 3 products. Let's draw them. So double bond here, plus, oh, of course, you do have your, don't forget your substituent in there. Double bond can be here, plus, double bond can be here. Now, which one is going to be the major? We didn't say which one is the major here. The major is going to be the most stable alkene, and the most stable alkene is the alkene that has the most substituents around the alkene. So this is the alkene. It's going to be 1, 2, and 3. This is a tri-substituted alkene. Here, that is going to be a di-substituted alkene, and again, a di-substituted alkene. So this is going to be my major product. So circle that, and that is going to be my major product. And these two are going to be my minor products because they are di-substituted alkenes. But between those two, this is going to be the most stable trans isomer, and that's going to be the least stable trans cis isomer. Now, between those 3 over here, now don't forget that this guy has 2 CH3s that are the same. So you have the possibility of cis and trans over there. Let's write them down. So your CH3s basically can either be on the same side or they can be on opposite sides. So this is on opposite sides. This is the trans, plus they can be on the same side, and that is going to say same side, whether they are both up or they are both down, it is the same. They are identical in there, because you can draw a plane of symmetry, so they are basically identical in there. So it's going to be a trans. This is going to be a cis in this case. So, so these are my my 4 products. Now, which one is going to be the most stable in there? Look at the degree of substitution around the carbon double bond carbon. So this is going to be 1, 2, and 3. It's going to be tri-substituted. That is going to be a di-substituted here. So let's write that down. This is a di-substituted. This guy over here is a tri-substituted. And this one here is a 1, 2, 3, and 4. This is a tetra. And that is a tetra. So definitely the tetra substituted are going to be the most stable. Now between these two, which one is going to be the most stable among them? It's definitely the trans. The trans is going to be the most stable. So let's go ahead and circle the trans, the tetra substituted trans, which is going to be the most stable in this case. Over here, I do have two different types of beta hydrogen. I have a beta hydrogen here and I have a beta hydrogen there. So my double bond can either be on this side or it can be on the other side. And in this case, here you go. So my double bond can either be here, plus my double bond can be here. And this one's going to be a disubstituted, so this is going to be the major product, it's going to be the minor product. With this one, with this example, my double bond can either be on the side or on the other side. I have two types of, no, actually not on the side, because here I don't have any hydrogen. I don't have any beta hydrogen. So there will be no elimination in here between this carbon and this carbon. So my elimination is only between this carbon and the carbon of the halogen. This is my only elimination. And I am going to end up having my alkene over here, and this is going to be my major product. Draw the major E2 elimination product from each of the following alkyl halides. Now the reaction, the question when it is asked like this, what I want from you is to show me the mechanism of the reaction. So I've already solved this over here. The first thing that you would need is to change this into a chair conformation, because since I'm asking you about the stereochemistry of the reaction, I want you to show me that the reaction normally happens whenever the halogen and the hydrogen are trans-diaxial with respect to each other. So the first thing you would need to do is change this into a chair conformation and make sure that the halogen is on the axial position. So it might be on the equatorial, you have to flip the chair, make it on the axial position. Once you make it on the axial position, choose the adjacent hydrogens that are trans and axial with respect to that chlorine, and those are going to be the ones where the base is going to attack. So here in this case, the base is going to come, it's going to attack that beta hydrogen, it's going to form a double bond, and the chlorine is going to leave. So when this happens, then you're going to end up having this as a product. This is your first product, or the base can come take this beta hydrogen, form a double bond, and halogen is going to leave. So my double bond is going to be on that side, is going to be the other alkene that is formed. Between those two, one of them is going to be the major product because it is a tri-substituted. This one is a disubstituted alkene. It's a disubstituted alkene because this is your alkene, right? So that alkene is basically connected to this carbon and to this carbon. So this is a disubstituted. This alkene is connected to 3 carbons over here. So this is going to be a tri-substituted. A tri-substituted is major. Same thing, you change this alkyl halide into a chair conformation. If the chlorine is in the equatorial position, just go ahead and do the flip, make it axial. And if once you make it axial, choose the adjacent hydrogen that is in the axial position. And it's that hydrogen here. In this example, I only have one adjacent hydrogen in the axial position. So I'm going to only have one alkene product in there. Just one alkene product. Base is going to come, take this alpha hydrogen or beta hydrogen, form a double bond, and the chlorine is going to leave. And I'm going to end up having this product in there. Draw the major E2 elimination product from each of the following. Show the detailed mechanism with the stereochemistry. So again, I'm just going to go ahead and change this into a chair conformation. Here you go. I want my chlorine to be down and to be on the axial position. So I'm going to choose my chlorine over there to be down. This is my chlorine that's down, and I want it to be on the axial position for the E2 to happen. So here you go. This is my chlorine is down. And then I'm going to move this way. So that is going to be carbon number 1. That is going to be carbon number 2. Carbon number 2 has the CH3, which is up. This means that the hydrogen is down. Okay? So there will be no elimination in here because I don't have a trans diaxial. I have a CH3 over here. It's carbon number 2, and then I have carbon number 3. Carbon number 3 has the ethyl group, which is up. Up means equatorial. So my ethyl group over here is here. It's on the equatorial. This means that my hydrogen is on the axial, but again, this is very far away from the chlorine. So pretty much that's it. Now I need to have my elimination in here. Elimination happens in presence of a base. So let's say if I have a base in there with a negative charge, a strong base, this is going to be my alpha carbon. Now I know that I have a beta carbon in here. It's going to be beta 1. This is going to be beta 2. Now elimination is not going to happen. This is beta 2 here. Elimination is not going to happen between alpha and beta 1 because on beta 1 my hydrogen is on the equatorial position. My elimination is going to happen between the alpha carbon and the beta 2 hydrogen because the beta 2 hydrogen is the one that is on the axial position. So the base is going to come, take that beta hydrogen, form a double bond, the halogen is going to leave. So my elimination product, this is the stereochemistry of the reaction. You're going to have a double bond in here, and then you're going to keep the same stereochemistry for all the substituents in there. This is equivalent to basically that cycle over here. Elimination could not happen on beta, basically on beta 1. Yeah, elimination couldn't happen on beta 1. Elimination happened on beta 2. So I formed a double bond between the alpha and beta 2. So this is going to be my product in there. And I'm left with the same substituents in here. I didn't do anything to those. So they stay in their place like that. So this is going to be my major elimination product in this case. E1 mechanism with E1. E1 is basically a slower reaction. It's normally it occurs with SN1 reaction. It uses a weak base. So all weakened nucleophiles are weak bases. So if you have a weakened nucleophile, it is also a weak base. So if whenever you have SN2 reaction, you have E1, or whenever you have SN1 reaction, you have E1 reaction. The E1 proceeds with a two-step mechanism. The first step is exactly the same as SN1. The halogen is going to leave. You create a carbocation, and once you create a carbocation, the difference now, you don't have a nucleophile because that water acts now as a base. Base takes the hydrogen, so base is going to take the beta hydrogen. So it's going to be my beta hydrogen in here adjacent to the carbocation. All of these are my beta hydrogens in there. So all of these are the same beta hydrogens, as you can see. So the base is going to come take the beta hydrogen and form a double bond. Now here I don't have a leaving group. The leaving group left at the beginning. The first step is normally the slow step, and the second step is the fast step. So the first step is the one that determines the rate of the reaction. So basically with E1, the rate depends on the concentration of the alkyl halide only. It doesn't depend on the strength of the base because the base is not used in the first step. It's used in the second step reaction. Okay, so this is just explaining how the mechanism happens. It is a two-step reaction in there where you start with your reactants, form a transition state in the first step. The first step is a slow step because its activation energy is larger than the second step. The second step is a faster step because it has a smaller activation energy, and then you get to your product in there. With respect to the alkyl halide has to be tertiary because don't forget that we are making a carbocation, and carbocations are more stable whenever they are tertiary carbocations. So E1 and E2, they share the same concept regarding the identity of the alkyl halide. The alkyl halide has to be tertiary. It reacts faster than secondary than primary. Now, with respect to the strength of the base, with E1 reaction, the base has to be a weak base, and it has to be neutral. All weak bases, these are neutral bases. These are going to favor E1 reactions. This is going to be different than E2. E2 favors stronger bases. Stronger bases are negatively charged bases. Now for the regioselectivity of E1, how to choose your major product is exactly the same. Go with the most substituted alkene. So the more substituted the alkene is, the major is the product. But please don't forget that you have rearrangement here. With this type of mechanism, E1, you are making a carbocation, so definitely you're going to end up having rearrangement. Do rearrangement. Every time you form a carbocation, make sure that you rearrange. And after you rearrange, just go ahead and allow the base to attack the beta hydrogen and form your alkene. One thing I want to mention in here for elimination reactions, the condition for elimination is heat. So if your reaction requires heat, then your major product is elimination, because heat means I am breaking bonds in there to form a pi bond. So the major product with heat is elimination. So for E1, it is a two-step reaction. It is a first order. My alkyl halide has to be tertiary, more stable than, or faster, or more stable than secondary than primary. With a primary alkyl halide, there is no E1 reaction, and there is no SN1 reaction. Okay, so with primary alkyl halide, there is no way I'm having either I1, E1, or SN1 reaction. Normally, whenever I have E1, I have SN1 with it. So we call this a contaminated reaction. It's not a clean product. So if you wish to have just the elimination product, you can't. You will get both products, so you have to isolate one from the other, either by extraction or by crystallization or any of the purification techniques, organic techniques in the lab. So comparing E2 to E1, the alkyl halide characteristics are the same. I need a tertiary alkyl halide to react compared to faster than a secondary alkyl halide than a primary alkyl halide with E2, same as E1. But this doesn't mean that primary alkyl halides doesn't do a reaction with E2. They do, but I need to use a bulky base. But with E1, primary alkyl halides can never ever react. So I would end up having no reaction because I cannot form a primary carbocation. Now, SN1 and E1 do occur together. SN2 and E2 occur together. So the rule says that the ones happen together, the twos happen together. There are some conditions that basically E2 happen alone without SN2, and there are cases where SN2 happens alone without E2. But with SN1 and E1, no, they do happen together every single time. So whenever you form an E1, you form an E2. Just to differentiate between a nucleophile and the base, the nucleophile adds to the partial or the positive charge carbon or to the electrophile. The base takes the hydrogen, the acidic hydrogen, and form a double bond. This is the difference in there between both mechanisms. Now, in the coming slides, these are just a summary for both chapters 6 and 7. I've combined everything here together. Whenever you have a reaction in there, just to know what type of mechanism you are going to go by. If you are working with primary alkyl halides, so let's start. So if you're starting with a primary alkyl halide and you're using a good nucleophile, I've listed all the good nucleophiles here. So good nucleophile is a nucleophile that has a negative charge. Now with all of these good nucleophiles in the primary alkyl halide, your product in this case is going to be only the SN2 product. That's it. So your product is going to be the substitution of product. So what type of substitution? SN2 mechanism. Now, the type of solvent that we use normally, it has to be polar product. So we don't prefer to use methanol because polar aprotic, I'm sorry, because methanol is polar protic, and polar product is going to decrease the rate of the reaction a little bit. It's going to slow it down, but the reaction can proceed to completion. The better solvent than methanol is acetone. So we prefer to have a basically a polar aprotic solvent. Methanol is a polar protic solvent, and that polar protic solvent will slow down the reaction, the SN2 reaction. It's not going to stop it, but it's going to slow it down. What determines if the reaction proceeds or not is the type of a nucleophile that you're using and the alkyl halide that you are using. The solvent either speeds up the reaction or slow it down, but normally it doesn't stop it. What stops the reaction from going to completion is the type of a nucleophile and the alkyl halide. So these two have to be compatible with each other so that the reaction proceeds by SN2. And for that reaction to go by SN2, it has to be a good nucleophile, it has to be a primary alkyl halide. Bulky bases. Now, if you're using bulky bases with a primary alkyl halide, then immediately you would need to use heat, and your product is going to be an E2 elimination. Immediately. So there will be no SN2. Why no SN2? Because this guy over here is not a nucleophilic. It's not even a nucleophile. It's just a base. So that base is going to come take the beta hydrogen, form a double bond, bromine is going to leave, and you're going to end up getting your E2 product. With this guy over here, now if you have a tertiary alkyl halide, now tertiary alkyl halide, depending on the type of base that you are working with or nucleophiles, it can go either by E2 mechanism or by SN1E1 mechanism. So we know that tertiary alkyl halides, they do undergo E2 mechanism. So if you're working with a tertiary alkyl halide and you're using a strong base, now I know that definitely there is no SN2. Why there is no SN2? Because SN2 cannot happen with a tertiary alkyl halide. So the mechanism is going to go precisely by E2, and that we call it a clean elimination. This means that your only product is elimination, and we use it too much whenever you want to synthesize an alkene, because you can go straight to your product in there. There will be no other byproducts, so the purification of this product will be easy. The list of strong bases that we can use with this tertiary alkyl halide to get the E2 product are all of these bases in here. Now, if you're using a weak nucleophile, neutral, so weak means neutral. So weak neutral nucleophiles or bases with the tertiary alkyl halide, then the mechanism is going to go by SN1 and E1, so you should show both products in there, SN1 and E1 products. For primary alkyl halides, remember that primary alkyl halides just happens with SN2 mechanism. If you're using a strong nucleophile, it's just SN2 in there. And if the nucleophile is small, like any of those, then the product is going to be SN2 product. But if it's bulky, then it's going to be an E2 product. Now for secondary alkyl halides, so as you can see here, I'm considering the cases. I did consider the case of tertiary alkyl halides, primary alkyl halides, and now we're considering the cases of secondary alkyl halides. Now for secondary alkyl halides, they can go by both, by either SN2E2, E2 alone, or SN1E1, based on the type of the base that I use or nucleophile that I use. So if I use a strong bases in nucleophiles, then in that case, we're going to end up having two products. One of them is going to be SN2, the other one's going to be E2. Now you're going to ask me which one is going to be the major, which one is going to be the minor. Well, it's so simple. If you have heat in the conditions, then E2 is going to be the major. If there's no heat, then SN2 is going to be the major. Okay? Now with a strong sterically hindered base, like this one over here, this is a strong base, this is a secondary alkyl halide, there is no way I can get substitution. No SN2, so it's just going to be E2. Now I am limiting myself to the 2 in here because this is a strong, it's negative, it's a strong. So if it's a strong, then it's a 2. Can be either E2 or SN2. So if it is not a nucleophile, it's definitely an E2 elimination. Now with weak nucleophiles or bases, so this guy is going to be a weak nucleophile. This is secondary. It has to go by both SN1 and E1 product. We've talked about these. I'll give you an introduction in chapter 6 about the other leaving groups. Now in chapter 8 we will talk more about these other leaving groups, but just remember that the weaker the base, the better leaving group it is. We do have here an example of a super good leaving group, which is the conjugate base of the trifolic acid. Another very good leaving group is the tosylate. It is the conjugate base of a very strong acid, so it's going to be a very weak base. And the mesylate. This is another example of a very good leaving group. So all of these leaving groups, these are better leaving groups than the halogens themselves because they came from more or stronger acids. They came from stronger acids, so they are weaker bases. So predicting the mechanism of the reaction, the mechanism of the reaction in there. This table in here summarizes the slides that I've said before. So primary alkyl halide, strong nucleophile, it's SN2. Strong bulky base, it is E2. Then you go with secondary, and then you go with a tertiary alkyl halide. What mechanism E1, E2, SN1, SN2 will occur in each reaction? So let's go ahead and draw the mechanism here. First thing I would look at is my type of a nucleophile. This is negative. So it is a strong nucleophile. So that is going to be a strong nucleophile. And it is a strong base. Whenever it's a strong nucleophile, it's a strong base unless it is bulky. If it's bulky, then it's only strong base. So if it is both, then it can act, since it's a strong, I can have either SN2 or I can have E2. But then I need to look at the alkyl halide and see if substitution is possible. This is a tertiary alkyl halide. SN2 cannot happen with tertiary alkyl halides. So my major product is going to be the E2 product in there. Okay, there will be no SN2. So let's write the mechanism of the reaction in this case. So with respect to the mechanism of the reaction, let me change the color in here. Okay, so for the mechanism of the reaction, I do have my halogen there. Okay, and I'm reacting it with the OCH2, CH3. This is going to be E2 elimination. It's going to be a concerted reaction. I do have only one type of beta hydrogen. All of these beta hydrogens are the same. So my base is going to come. It's going to take the beta hydrogen, form a double bond, and the chlorine is going to leave. So I am going to end up getting my E2 product, and the E2 product is going to look like this. This is going to be my E2 product in there. That is going to be the only E2 product in the reaction. Now notice whenever I have heat, then my product is going to go towards elimination, and this is always the case. If I don't have heat, then I have to write down all of the products, the substitution and the elimination, and normally the major product will be the substitution product and not the elimination product, but you have to list down all your products though. So with water is a weak nucleophile, and it is a weak base. Please remember that water here is my nucleophile, and I didn't use any solvent, so it acts also as a solvent in there. Whenever you have a weak nucleophile, it acts as a weak base, so the mechanism is going to be both SN1 plus E1. So let's start the mechanism. First step is going to be common for both SN1 and E1. Iodine is going to leave, and I'm going to end up having my basically carbocation. Okay. Um, Now this carbocation in here, and this is a chiral center, by the way. So I'm going to end up having a racemic mixture. Now let's consider the substitution of product first and then the elimination of product. So for the SN1 product, we're going to have water, and water is going to come and it's going to attack either from this side or from the other side. And when it does, we're going to end up having two products in here. We're going to end up having the, okay, I'm going to let these two be in plane, that's easier. And then if hydrogen is behind, then the water is going to be in front. The water is going to attack and it's going to be in front here. Plus, there you go. And if the hydrogen here is going to be in front, then the water is going to attack and be behind. This is going to be your second product, but not yet, because it's still charged. So I have to use another water molecule in here for both of them. Since water is my nucleophile, then water acts as a solvent too. Plus, of course, my leaving group, which is the iodine. I could have used the I minus in order to take that extra hydrogen, so whatever you want. So water here is going to come. It's going to take that extra hydrogen by the acid-base reaction, form a lone pair. Again, it's going to come here, take that extra hydrogen and form a lone pair on the oxygen. So you're going to end up basically getting two SN1 products. You have to show the stereochemistry of the reaction, as I'm showing it over here, showing the retention and the inversion in configuration. So that is a hydrogen plus my second product in there. You do have a hydrogen up and an OH and down, and both are going to be my SN1 products. Okay, so these two are going to be my SN1 products, and you have to show them both, and both are going to be the major products for substitution. Since I don't have heat in there, this is going to be my major product, but I have to continue and do my E1 product. So again, the ones happen together. So with the E1 product, I have my carbocation. Now I'm going to use water as my base. Oh, first, see that carbocation, I didn't do any rearrangement in here because I should have done a rearrangement, by the way. I should have done a rearrangement in here. Let me change the question. We will do a rearrangement later on. So let me take this out, take this out, take this out so that it is right. But I could have done a rearrangement over here and moved the positive charge there, and then allowed the water to attack. But anyways, so we changed the question in there so that we won't do rearrangement. So water here can act as a base, and if water acts as a base now, then my mechanism is going to be an E1 mechanism. So if it's an E1 mechanism, that base now is gonna come. How many beta hydrogens do I have? This is one beta hydrogen, and this here is another beta hydrogen. You see that? Two beta hydrogens. So the base can come, take this beta hydrogen, form a double bond, and I'm going to end up getting my first E1 product, plus the base can come take this beta hydrogen, form a double bond, and I'm going to end up getting my second E1 product. We draw it right over here. So that is my second E1 product there. So 1, 2, 3. This is 1, 2, 3. So this is good. So between those two, Which one is going to be the major product? This one is a tri-substituted, and this guy is a di-substituted. So definitely this one is going to be a major E1 product. Now between, this is going to be my products in there. So this is going to be a product, this is going to be a product. These are all my SN1 and E1 products. This is going to be a product and this is going to be a product. So I'm going to end up having 4 products in there. 2 SN1s, 2 E1s. Since I don't have heat, then both of those are going to be my major product. If I had heat, then this guy is going to be my major product. But you have to show all 4 and then point out the major. Okay? Unless I ask you, what is the major product? Just show the major product, then you don't have to show any of the rest, just show the major product. But here I am asking you to draw all possible products and then label the major one. This one requires rearrangement. It's the same SN1 E1. So this is going to be water, methanol over there. So methanol is going to be my nucleophile. Water is going to be my solvent. So that's going to be my solvent. Methanol is going to be my nucleophile or base. That is a weak nucleophile. It is a weak base. So my mechanism is going to be both SN1 plus E1. So first thing you do, you create your carbocation. Okay, so don't do like I did in the example before. Once you create your carbocation, just ask yourself, can I make it more stable? Oh yes, I can. By simply moving that CH3, moving it here. So when you move the CH3, you're going to end up having a CH3 over here, and then a plus a charge over there. That is tertiary. That was basically, that was still a tertiary in there. So you have a tertiary here, you have a tertiary there. Let's see. This is a 1, 2, and a 3. This is a 1, 2, and a 3. So both are going to be tertiary in here. So no need for rearrangement here in this case because you're moving from a tertiary to a tertiary. So again, I'm just gonna take this out, take this out. No need for rearrangement. Both are gonna be tertiary. So no need for any rearrangement. I'm gonna leave it like this. When you do rearrangement, you do it from a secondary to a tertiary. Right now, this is a tertiary alkyl chloride. So when chlorine leaves, you're going to end up getting a tertiary carbocation. No need for rearrangement at all. So let's proceed. We're going to proceed first with the substitution. So proceeding with the substitution in there with the SN1. This is methanol. So now methanol is going to be my nucleophile. This is my weak nucleophile. It's going to go by SN1 reaction. So the methanol is going to attack from the top, or it's going to attack from the bottom. Now since this one is a cycle, even though it's not a chiral center, we can attack it from top and bottom. So you're going to show over here, here you go, the attack. So let's make these two in plane. So if the attack of methanol is behind, then this group over here, the whole thing is going to be in front. Drawing stereochemistry is really important. Okay. Now, even though this is not a chiral center over here because these groups are the same, but still, I mean, since it's a cycle, you can show the tetrahedral geometry. Plus, it's fine. You can just practice this and show the tetrahedral geometry in there. So you have this, and then methanol can be on the in front, plus there. Now I'm gonna use water as a solvent in order to pick up any extra hydrogen in the reaction. So now my product here, so water is gonna come, take those extra hydrogens in here and add electrons to the oxygen, so that I'm going to end up getting my 2 substitution of products. My first substitution of product is going to be this OCH3 plus my second substitution of product is going to be, I just want to note that these two products are the same because this is not a chiral center. These two are the same. So if you don't want to go with that stereochemistry in here with the showing the wedges and the dashes, it's okay. It's okay by me. You can show them as straight lines and it's fine. These two are the same because there is no chiral center over there. And this is the SN1 product. With respect to the E1 products, I'm just going to go from here. The methanol now is going to act as a base. And that base is going to come, it's going to take my alpha hydrogen, my beta hydrogen. I don't have any beta hydrogen here, but I do have a beta hydrogen here. These two beta hydrogens are the same. Okay, they are the same. So my base is going to come, it's going to take that beta hydrogen, it's going to form a double bond, and I'm going to end up getting my product. Whether the double bond here or the double bond there, it's honestly, it's the same. So that is going to be my only E1 product. That's it. This is a primary alkyl halide. This is a strong bulky base. This is going to be a strong, it's a bulky base. So if it is a strong bulky base, then that bulky base is going to attack as a base, not a nucleophile. So the mechanism is going to be E2 only. So the base is going to come. This is the idea over here. Base is gonna come, it's gonna take my beta hydrogen, form a double bond, and the bromine is gonna leave. I don't worry about stereochemistry unless I have a cyclohexane, then I need the hydrogen and the halogen to be trans-diaxial with respect to each other. Other than that, I don't care about stereochemistry. Just make the base, take the hydrogen, form a double bond, and the bromine leave. And you're gonna end up getting your alkene product in that case, and that is going to be my alkene product over here. Okay, I believe that I had a CH3 over there too. It's gonna be my alkene product. So over here, let's go ahead, and this is a strong base. So strong base is strong nucleophile, both. Strong base is strong nucleophile. This is acetone, this is a secondary. So I'm gonna end up having SN2 plus E2. So I'm gonna end up having both products in there. Let's start with the SN2. I always start with the SN2 product. So the base over here is going to be my base. This is a chiral center. So the base over here is going to attack. Let's say if I had the bromine up, then the base is going to come and it's going to attack from the opposite side of the leaving group, and the bromine is going to leave. So the reaction for the SN2 is going to proceed with inversion in configuration, and the OH is going to be behind. Okay? If I did not specify the orientation of the bromine, it's fine. You can make it a straight line in here. As the OH, you don't have to show the stereochemistry of the reaction. So this is with respect to the SN2. Now with respect to the E2, I do have how many beta hydrogens here? I do have a beta hydrogen here, and I do have a beta hydrogen in there. Now this is a cyclohexane, but since it doesn't have any substituents, each one of these hydrocarbons, beta carbons, have two hydrogens. Definitely one of them is going to be axial. So I can have the bromine to be on the axial, hydrogen to be on the axial, I can have the trans-diaxial in there. So the base is going to come, and that base is going to take the beta hydrogen, form a double bond, bromine is going to leave, and can do the same thing to the other carbon or to the other beta hydrogen. So with the E2, I'm going to end up having two products. I'm going to end up having my alkene here, plus I'm going to end up having my alkene there. And these two are different because of the existence of the CH3 at the bottom in here. That's going to make these two products completely different from each other. So these are going to be both E2 products, and this is going to be the SN2 product in here. So if I had heat, then immediately my elimination the E2 products are going to be favored over the SN2 product. Which one is going to be major? The more substituted one is going to be major. Now on this side, both are di substituted. This one is di substituted and this one is di substituted. But this alkene is closer, its adjacent carbon is closer to this branched carbon in here. So I'm going to say this one is major compared to this structure over here. But it's fine if you find them the same degree of substitution. You can say that both of them are major. Okay, you don't have to favor one over the other. You can simply say that both of them, since they are di-substituted, this is my alkene, this is my alkene, so since they are both di-substituted, they are both major E2 products. This is a primary alkyl halide. Now this nucleophile in here, it doesn't act as a base. It's more a nucleophile than a base. So it's a good nucleophile, it's a weak base. So how did I know? It's in one of the slides in here. Okay, it's in, where is it? It's probably, here you go. It's here, the N3 negative. That is a strong nucleophile. It's a good nucleophile, and it is it's a weaker base. So with N3 in here, it favors basically the substitution, the SN2 product only, which is here. I'm just going to add to those the N3 negative. So with the N3 negative primary alkyl halide, that product is going to be just the SN2 product. So you're going to end up having SN2. I don't have any chiral center in here, so I don't proceed with inversion. It's just the replacement of the bromine with the N3. But please pay attention to your carbons. I have 4 carbons in here. I have 4 carbons in there. Here you go. So you just replace the bromine with the N3 and keep your carbons the same. Draw a stepwise mechanism of the following reaction. So with the following reaction, I wrote down all the stereoisomers though, but I just want you to check this out and see. Well, I have my water as a nucleophile. This is a tertiary alkyl halide. This is a weak nucleophile and a weak base. So my mechanism is going to be an E1 mechanism, and all of those are going to be an SN1 mechanism. Since I'm creating a chiral center, which is at the end, I'm going to end up getting 2 chiral centers. This is a chiral center and this is a chiral center. So I'm going to end up having 4 stereoisomers in this case, 2 to the n. So 2 chiral centers, 4 stereoisomers. These are my 4 stereoisomers there for the substitution. These 2 are going to be mirror images of each other. These 2 are going to be mirror images of each other. And a combination of those are going to be diastereomers. So bromine is going to leave. I am going to end up getting my carbocation. Carbocation already is tertiary, so I'm not doing anything in here. I'm proceeding. Take water. Let's start with the SN1 first. So water is going to attack, and when water attacks, water is going to attack either from the left or from the right or top or behind. It doesn't matter the terms. So if water attacks from behind, then that is going to be it. If water attacks from the top, then that's going to be it. And remember that if water attacks from behind, then this CH3 is going to be in front, and vice versa. And then since I'm using water, I have to use it again, so that to deprotonate, take the extra hydrogen out in order to be left with the OH at the end. Now, just remember one thing, that I didn't mention this. Say anything about the stereochemistry of the CH3. So that CH3 in here can either be behind or it can be in front. So just like checking writing the options. So if the CH3 is in front, I can have my water attacking from behind or in front. And if CH3 is behind, also I can have my water attacking from front and from behind. So just consider all the cases in there to get the stereoisomers, the 4 stereoisomers for my 2 chiral centers. So this is going to be my SN1 and this is going to be my E1 products. The last reaction that I want to talk about is the elimination, is the E2 reactions that are used in order to synthesize, to make triple bonds. So far we've used alkyl halides with strong bases or weak bases in order to make double bonds. Now we can use basically dihalides, not a single alkyl halide, a dihalide, in order to make 2 elimination reactions. And in this case, we're going to end up forming a triple bond. This is how the reaction is going to proceed. For elimination to happen to lead to a triple bond, you would need a very, 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 very strong base. Very strong base. The base can be either a bulky base like LDA, like potassium tertiary butoxide, or we can use sodium amide. This is a very strong base. It is a nitrogen base, so it is very basic. This guy here, it's very basic, and it's a convenient base to use in these types of reactions. Since it's negative, it is strong, so the mechanism is going to proceed by E2. You can make triple bonds either by starting with dihalides that are either on adjacent carbons, we call them vicinal, or they are on the same carbon, we call them geminal. The idea is you are performing 2 sets of eliminations. Each set of elimination you are removing an HX. Each set of elimination you are removing an HX. Same thing over here, same thing over there. So you're doing this thing in 2 steps. The first step, the base is going to come, take the beta hydrogen, form a double bond, the halogen is going to leave. So again, base takes the beta hydrogen. So in this case, I'm considering this is the alpha carbon, that is the beta hydrogen. So the base taking the beta hydrogen, forming a double bond, halogen is going to leave. You do it again. So if this is the alpha carbon now, this is going to be the beta hydrogen. So base is going to come take the beta hydrogen, form a triple bond, and the halogen is going to leave. I could stop at the vinyl halide, and but in this case, I mean, I have to proceed with my product to be a triple bond. But if you don't want a triple bond, you could have stopped by simply adding just 1 mole of the sodium amide, and then you're going to end up getting your vinyl halide. We're going to do the same thing for the geminal halide, and this is how we make our triple bond. Bases to use, either the amide or the potassium tertiary butoxide, any one of those, or we can use LDA or LDA. So any one of those is basically a good base in order to make the triple bond. So this is the summary of the reaction in here, where basically it's an example. I am having basically the geminal halide or the vicinal halide, dihalide, and I am using a base in here. The base in either one of these cases is in excess. It's always in excess because this is a 2-step reaction, and every time I'm doing an elimination, I'm taking an H and a halogen. Each time I'm doing it, taking an H and a halogen, and I'm going to end up having my triple bond. Last slide. So draw the alkyne in this case. So my alkyne, this is going to be my base. Locate your beta hydrogen. So this is going to be my beta hydrogen to this alpha carbon, and that is going to be my beta hydrogen to this alpha carbon. So my base is going to come, take that hydrogen, form a double bond. Halogen is going to leave. This is the first. So I'm going to end up having a double bond in here, and then proceed further. Base is going to come. It's going to take my hydrogen, form a double bond, and the halogen is going to leave. So it's going to be a triple bond. So my triple bond that I'm going to form in here is basically between the 2 dihalides. So that is going to be my triple bond. So notice here I do have my chlorines. My chlorines are going to be on the same carbon. So my chlorines in this case, they are on the same carbon, and if they are on the same carbon, this is a gymnal dihalide. So they are gymnal dihalides again. These are the hydrogens that I'm working with. So the base is going to come, take the hydrogen, form a double bond, chlorine is going to leave, and it's going to come again, take the hydrogen, form a double bond, a triple bond, and the chlorine is going to leave. So my triple bonds are going to be here. Okay, now here I do have two sets of beta hydrogens. This is one, this is two. Okay, of course I do have one over here, but I'm going to use just two. Or I can use these beta hydrogens over here. So my triple bond can either be here or it can be there. So I'm going to end up having plus. Okay, so and I'm going to end up having two products in there. One more thing that I want to say. Okay, if you have a triple bond, just let's draw it right. So if you have a triple bond, this is linear. So you're going to end up having a CH3 over here and a CH3 over there. This is not it is not an angle. It is linear though. So it's going to look like that. And same thing over here. I should have drawn it like this. This is linear. That part is linear. And then you have it like this. Let's me make sure that I put this right. Same thing over here. Whenever you make a triple bond, just make sure that the triple bond together with the carbon that is connected to it, these are linear over there. So this part is linear, and here together with this carbon, now these two carbons in there, I can put them as bent. So this carbon here, it's carbon there. Same thing here. Okay, same thing over here. So you are making a triple bond. So okay, so here you go. And then let me write it like this. And then this is going to be my triple bond. And then I'm having a triple bond here, and then I'm having an ethyl group in here. So this is going to be my ethyl group. So that the whole thing is linear. See, this carbon and this carbon, these are linear carbons. So it's going to be linear over here. So it's going to be the product for the elimination reaction, the alkyne product for a two-step elimination reaction using a very strong base with both gymnal and vicinal dihalides.